This lab will look at a magnet falling through a solenoid and the governing principles behind it. The goals of this lab are to gain an understanding of Faraday's law, explore how Faraday's law can result in the creation of a second magnetic field and how it changes as the initial magnetic field changes, and improve one's ability to model complex systems using interactions such as Faraday's law, gravity, magnetic fields, magnetic forces, and currents. To start, it is important to understand that Faraday's law states that any change in magnetic field acting on a loop of conducting material will result in a voltage being induced. This is the core principle in this lab, but in order to utilize it, other concepts and formulas will have to be used, such as magnetic field, which can be calculated using this equation. From this, the magnetic flux can be determined, and a derivative can be found to find the change in magnetic flux through time. This magnitude is equal to the EMF on the surrounding loop, and if a resistance is present, a current is established which ultimately creates an opposing magnetic force on the loop, and thus on the source of the original magnetic field also. To begin this lab, an aluminum foil roll is needed as well as a magnet. The foil roll used was a foot tall and 1/4 of an inch thick and had an inner diameter of 1 1/8 inches. Once the north and south poles of the magnet were determined, the magnet was dropped down the aluminum foil tube while a camera recorded the drop. This was repeated 5 times, and the videos were then examined on a smaller time scale to find the duration of time it took for the magnet to fall through the aluminum foil. Ultimately, it took the magnet a noticeably larger amount of time to fall through the aluminum foil than it would without the foil present. When the average of the 5 trials was taken, it was determined that it took the magnet approximately 1.21 seconds to fall through. Now, in order to examine this process further, a computer model is used in which the initial values found during the experiment are inputted. Then, after other initial values and variables are set, a cylinder representing the magnet and a hollow cylinder made from many rings to represent the aluminum foil tube is created. Next, a function is created that will be used to calculate magnetic field created by the magnet at a location. A function is also created to calculate the flux from the magnet on a ring, and booleans are created to determine when the magnet is in the tube and is leaving the tube to give the overall time taken to fall. Next, a while loop is created that runs while the bar is above the bottom of the tube and the constant force of gravity is set. As this while loop progresses, it performs calculations at every ring inside the tube, first calculating distances, then magnetic fields, then magnetic forces on the loops in the y direction, and adding the magnitudes to the total force on the magnet, as Newton's third law explains that the forces are equal and opposite. After this for loop has run, the gravitational and magnetic forces are summed, and the velocity and position vectors are updated using this net force and the time step. Velocity is then plotted, and this repeats until the magnet reaches the bottom of the tube. Finally, the total time needed for it to make it through the tube is printed. When this code is run, it can be seen that it takes 1.218 seconds to make it all the way through. Furthermore, it can be seen that red indicates current flow in the counterclockwise direction from above, since its magnitude increases from above the magnet, meaning that the change in flux is in the negative direction. Thus, to oppose this change in flux, a magnetic field is created pointing upwards, which creates a current in the counterclockwise direction. It can be shown in a similar manner that blue indicates current flowing in the clockwise direction. We can also see from computational model or from the physical experiment that by reversing the magnet's poles, the dynamics of the systems are unaffected, as it still takes the same amount of time to fall through the tube. This makes sense as the magnetic force is induced by the magnet itself and will therefore change with the magnet, resulting in the same forces despite orientation. Furthermore, to improve this model, the delta T can be shortened and the tube can be broken up into even more pieces to make this model even more accurate. By looking at the velocity versus time graph, it can be seen that the magnet initially falls with a downward acceleration, but eventually that acceleration is cancelled out and the velocity levels out until it reaches near the end of the tube. When this velocity levels out, it means that the force of gravity is equal to the force created from Faraday's law, the aluminum foil, and the resulting magnetic force on the magnet. It is also interesting to imagine what would happen if the resistivity of the foil went as close to zero as possible. Since resistivity is directly proportional to resistance, which is inversely proportional to current, and thus inversely proportional to magnetic force, the magnetic force should get closer and closer to infinity. Also, it is worth wondering what would happen if holes were cut into our model of the aluminum foil. In this case, some of the rings would be incomplete, and thus current would not be able to flow through them. Without the current flowing through them, there would be no magnetic force resulting on the magnet, and thus the total magnetic force on the magnet would overall decrease. This would result in the magnet falling faster.